Hi everyone, welcome to CAIE Science, and today we will be solving the remaining paper of May-June 2022 for variant 4.1 and variant 4.3 of 970. In part 1, we did 4 questions. Okay, now today we will be continuing from question number 5. Okay, compare the relative acidities of benzoic acid, phenyl methanol, and phenol. And user reasoning. Okay, so in benzoic acid, this is the benzoic acid. Then you have phenyl methanol. Okay, this is phenyl methanol, and then you have this phenol. Okay, so now the basis acidity is uh, you can say the acidity basis on the uh, how easily a substance loses a proton and the stability of conjugate. So here we will see which of three of them will easily lose the uh, proton, or you can say H plus ion. Okay, so here this OH bond, this is the OH bond, and in this bond hydrogen is partial positive and oxygen is partial negative because oxygen is electronegative, more electronegative. And in this phenol, the lone pair on oxygen is delocalized into ring. Okay, so there are less electrons in this available to oxygen, so it will take more electrons from hydrogen. Okay, so there will be more polarization. Okay, so this phenol has more polarization. Okay, now we will compare this phenol with benzoic acid and phenyl methanol. So in benzoic acid, there are two electronegative groups attached. Okay, in phenol, there is only one electronegative group attached. Okay, and there are two electronegative groups attached. Okay, this oxygen will take electrons from carbon, and this oxygen will also no, this oxygen will take electrons from hydrogen in OH bond. Okay, like this, and the lone pair of oxygen is delocalized in this structure. Okay, this structure. Okay, become part of delocalization. So the OH bond is weakened because the lone pair on oxygen is now less available to oxygen. So there is more polarization and the bond is weakened. Okay. So in benzoic acid, there is more polarization as compared to in phenol. So benzoic acid is more acidic. Okay. And as you can see, carboxylic acid is more uh, acidic than the alcohols or OH groups. Okay. Because the carbo carboxylate group has a greater delocalization. So OH bond is weakened, and there are two electronegative groups attached, which are both oxygens. Okay, so we have benzoic acid. Now we will compare which of them, phenol or phenyl methanol, which of them is more acidic. So here, this alkyl group, alkyl groups, you know that they are electron donating groups, so it will donate electrons to OH. O. So this there will be less polarization in the OH bond. So the OH bond will be strengthened. Okay. So this is less acidic than phenol. Okay. So because in this phenyl methanol, the proton will be difficult to remove. Okay. So then we have phenol, and lastly, least acidic is phenyl methanol. And what is the reason? In benzoic acid, negative, there is negative inductive effect of carbonyl group. Okay, so OH bond is weakened. Okay, then in phenol lone pair on oxygen become is delocalized in ring into ring. So OH bond is weakened. Okay, and lastly we have phenyl methanol. In phenyl methanol, positive inductive effect of alkyl group. Okay, or you can say CH2 group. Okay, so OH bond is strengthened. OH bond is strengthened. Okay, each explanation has a 1 mark. Okay, so you will get a total of 3 marks. Okay, part B, a series of 9 separate experiments is carried out as shown in table 5.1. Complete the table by placing a tick in the relevant boxes if a reaction occurs. Place a cross in the box if no reaction occurs. Okay, so sodium with benzoic acid. The sodium benzoic is an acid, and acid reacts with metals to form hydrogen gas. So it will react with benzoic acid, sodium. Okay, so yes, the reaction will occur. Okay, then sodium with phenyl methanol. Okay, so with phenyl methanol, I'm trying the structures here again. Benzoic acid, then we have phenol, and then we have phenyl methanol. Okay, so sodium will react with benzoic acid, and this H group will be replaced by Na, sodium. Okay, and it will form a salt, sodium benzoate. Okay, and phenyl methanol will also react with sodium, and this H group will be substituted with Na. So yes, the reaction will occur, and the reaction will also occur with phenol. Now the sodium hydroxide, this is a strong base, and this will react with benzoic acid because benzoic is strong enough to react with sodium hydroxide. Okay, so yes, the reaction will occur with sodium benzoic acid. With phenol, yes, the reaction will occur, but with phenyl methanol, oh sorry, this is phenyl methanol. Okay, with phenyl methanol, no reaction occurs, and with phenol, the reaction occurs because uh, phenol, this OH lone pair on this O group is delocalized into ring. So there is a more delocalization in the ring, and you can say the delocalization of the ring is extended. Okay? So it attracts electrophiles better, and it becomes more reactive. Okay, so yes, it will react, but in this OH group, phenyl methanol, the OH bond is weaker, so it will not react with sodium hydroxide. This phenyl methanol is not strong enough to react with sodium hydroxide, and yes, it will not react with sodium carbonate, nor will phenol react with sodium carbonate, but benzoic acid will react because this is an acid, and acids react with carbonates from carbon dioxide, water, and a salt. Okay, so how you can differentiate between benzoic acid and phenol? You can differentiate by reacting them with sodium carbonate. So you will know that either it is a phenol or an acid. Okay, because phenol does not react with sodium carbonate. Okay, part C, benzoyl chloride can be synthesized by reaction of benzoic acid with PCl5 or SOCl2. Complete the equations for these reactions. Okay, so PCl5, and then it will form POCl3. These equations you have to remember them. Okay, these reactions are very important, so you must memorize them, and there you will balance them. These are already balanced. Okay, okay. So now part 2, use your answer to C1 to suggest why it is easier to isolate a pure form benzoyl chloride from reaction 2 compared to reaction 1. So why it is more preferable to form a pure benzoyl chloride from reaction 2, because the you can see that the all byproducts are gaseous. Okay, this is hydrogen chloride, this is gaseous, and sulfur dioxide is also gaseous, but this POCl3, it is not a gas, it is a liquid. Okay, so you have to separate benzoyl chloride from reaction 1, but there is no need for separation in reaction 2. Okay, so you can write all the byproducts are gaseous. Okay, moving towards next part, part D. Benzoyl chloride is hydrolyzed by water at room temperature to form benzoic acid. Complete the diagram to show the mechanism for the reaction between benzoyl chloride and water. Okay, include charges, dipole and lone pairs of electrons and curly arrows. Okay, so here you have to show charges. This oxygen is more electronegative and it will take electrons from the carbon, so it will be a partial negative and carbon will be partial positive. Okay, and this lone pair on oxygen will attack this partially positive carbon. Okay, and it will form an intermediate, and the intermediate will be this one, like this. You will have this OH group attached. Okay, and it will have a plus charge. These mechanisms are very important, so you have to remember them. Okay, and then this negative charge, this double bond which was broken, will again will donate its electrons to carbon, and this chlorine will take electrons from carbon. Okay, so then you have will get the benzoic acid. Okay, so this is the mechanism for this reaction. Okay, then the type of mechanism you shown in D1. Okay, so what type of mechanism is this? This is the addition elimination. Okay, addition elimination, because you can see that in first step this water here is attached added to this benzoyl chloride. Okay, and then in second step, this Cl group and this H group are removed. Okay, so it will again form benzoyl chloride, so it is eliminated. Okay, so this is addition elimination reaction. Okay, part E, acyl chloride reacts with sodium carboxylates to form acid anhydrides as shown in figure 5.1. Okay. Acyl chlorides and sodium carboxylates, they react together to form acid anhydride. The condensation polymers polyanhydride. So this is the acid anhydride group. Okay, this you can see in this part. Now what is it is saying? The condensation polymers polyanhydrates and polyesters are formed by similar methods. The repeat unit of polyanhydride is shown in figure 5.2. Use figure 5.1 and 5.2 to suggest the structures of two monomers used to make this polyanhydride. Okay, so you can see from figure 5.1 that this part is your first monomer and this part is your second monomer. Okay, and on this you can draw like this. You can, if you are given only this part and this polymer acid anhydride, and you are not given uh, any of these monomers, so you can write it as this is Cl or NaONA plus carbon double bond R group, and then you have a Cl group. Okay, so you, these both would be possible if you wouldn't have been given these uh, formulas. Okay, so now you can see that this part is your first monomer, and now this part here will be your second monomer. Okay, so firstly I'm drawing this bigger monomer which has rings attached. Okay, so uh, you can draw it in a skeletal formula, which will be an easier way to draw. Okay, so like this, and like this. Okay, I am considering that this Cl group is attached on this monomer. Okay, you can add this On group as well here. Okay, and then we have a second monomer which is uh, this monomer. Okay, and you can switch ONA group, these groups can be switched between these monomers. Okay, it does not matter. Okay, so these both are possibilities. Okay, so these are your monomers. Part 2, polyanhydrates are biodegradable. Okay, so just how this polyanhydrate can be degraded. Okay, you degrade these larger polymers by hydrolysis, and the hydrolysis is you can, it can be an acidic hydrolysis or basic hydrolysis. Okay, so you, how you degrade them? By hydrolysis. Okay, you can simply just write hydrolysis, by hydrolysis. Question number 6, describe what is meant by racemic mixture. So the racemic mixture is a mixture which contains equal amounts of each optical isomerism. A mixture containing equal amounts of each optical isomerism. Optical isomer. Okay. Part B. Asparagine is an amino acid that contains chiral carbon atom, okay, and displays stereoisomerism. Separate samples of asparagine are dissolved in CdCl3 and analyzed using carbon 13 and proton NMR spectroscope. Asparagine is shown. Predict number of peaks seen in um, carbon 13 and proton NMR spectra of asparagine. Okay, so um, in carbon 13, number of peaks, how many number of peaks? So you have to check the environment of carbon. Okay, how many different environments are there? So the first environment is this carbon, then this carbon is in different environment, and because this is attached to two hydrogen groups, then this carbon is also in different environment because there is no carbon double bond O. Okay, and this carbon is also in different environments. So how many peaks will be shown in carbon 13? 4 peaks. Okay, then you have proton NMR. Now you have to check the um, uh, environment of hydrogen. Okay, so how many environments of hydrogen are there? Okay, this is the first environment, hydrogen. Then you have this second, then you have this third environment, fourth environment, and this is your fifth environment. So how many peaks will be there? There will be 5 peaks. Okay, part C. The isoelectric point of asparagine ASN is at pH 5.4. Okay, describe what is meant by isoelectric. So this is the pH at which an amino acid exists as a zwitterine, or an amino acid has no overall charge, because in amino acid you have a carboxylic group and this is amine group, sorry, and at this in this amino acid, this amino acid usually occurs as uh, zwitterine. Okay, so there is an acid base reaction within the molecule. Okay, so this is your zwitterine. This could be R groups. Okay, so this is your zwitterine. Okay, so this positive and negative charge, this is a zwitterine, and in this you have positive and negative charges, so there is no overall charge, or okay, and or a molecule exists as a zwitter point. So this molecule zwitterine is formed at isoelectric point, okay, which is a pH at which, so you can write this, the pH at which an amino acid exists as zwitterine. Okay, or the pH at which amino acid has no overall charge. Draw the structure of asparagine at pH 1.0. Okay, so you have to remember that the pH below this isoelectric point will give you the positive charge. Okay, so the structure of asparagine, like this is the structure. Okay, I'm drawing this again. this. Like now you will have this positive charge. Okay, you have to remember that this pH below isoelectric point will give you the positive charge because this acid will form. Okay, so that's why the pH is decreased. Okay, this carboxylic acid is formed. Okay, part D, aspergine can polymerize to form poly and polyaspergine. Okay, draw the structure of polyaspergine showing two repeat units. The peptide linkage should be shown. Okay, so this could form a polyamide. Okay, because you can see that there is an amine group and carboxylic group. Okay, so this can form a polyamide. Okay, and what will be the structure of this polymer? So I, if I draw this structure, rearrange the structure. Okay, so you will have C CH3 and C double bond O NH2 group and H group, then you will have amine group. Okay, so I have just redrawn and rearranged the structure. Okay, so which will make you easier to form this polymer. Okay, now so now you have to show the two repeat units. Okay, carbon, this will be this, like this group will be unchanged. Okay, so we have to keep this same. Now this amine group will form NH group and this will be your amide linkage, like this is your amide linkage, and then you will have a second monomer. Okay, so these are your two repeat units. Okay, and this is your peptide linkage, and this is also an amide group. Okay, you know that. Part E, the isoelectric point of lysine is at pH 9.8. Okay, and the structure of lysine is given to you. A mixture of dipeptides, lysine, lysaspergine, and two of its constituent amino acids, aspergine and lysine, is analyzed by electrophoresis. Okay, using a buffer solution at pH 5, uh, pH of 5. Okay, the results obtained are shown in figure 6.3. So you have suggest the identities of four species responsible for spots E, F, and G. Okay, explain your answer. So you have to find which one is responsible for these spots. Okay, so you have aspergine. Okay, this aspergine has the isoelectric point at pH 5.4. Okay, SN, and this isoelectric point of this is at 5.4. Okay, then you have a lysine, and then you have lysaspergine. Okay, lysaspergine. Okay, and this isoelectric point of 9 lysine is 9.8, and you don't know this isoelectric point of lysaspergine. Okay, so and we don't need this, we have just to find which is aspargine and which is lysine, then the third one is automatically you can know that this one is a lysaspargine. Okay, so this these all are attracted to a negative cathode. Okay, so you can tell that these all are positively charged. Okay, that's why they are attracted to negative charge. Okay, and this buffer solution is at pH of 5. Okay, the pH is 5, and you can see that this aspargine has a isoelectric point at 5.4. So it might be possible that it is not changed into a positively charged ion. Okay, it it is possible that it may be neutral. Okay, because this pH of aspargine 5.4 is very close to this pH of buffer solution. Okay, so this is aspargine is nearly uncharged. Okay, so and this mixture is applied here where there is no charge, and E is very closer to this, so it means this E spot is due to aspargine. Okay, I hope I could clarify. Then you have lysine. Okay, there is a huge difference between lysine isoelectric point of an lysine and pH of buffer solution. Okay, so it will form positive charge. Okay, and now you have to decide which of them will be F and G. So if you see, lysine has a charge of plus and aspargine has a charge, let's say a zero, neutral. Okay, so these both aspargine lysaspargine and lysine have both have same charge. So now you have to see which one of them has greater MR. So definitely lysaspargine has a greater MR, so it will move less. Okay, so F is due to lysaspargine. Okay, and then we have lysine. So now let's explain this. How you will explain, and you can say that aspargine is nearly uncharged. That's why you have a point at uncharged. Okay, that's why there is a E is aspargine, and then you can say that this lysaspargine has greater MR. Okay, so that's why this is F, and then we have G as lysine. Part 4. Okay, so part 4, this thin layer and gas liquid chromatography can be used to analyze mixtures of substances. Okay, each type of chromatography makes use of stationary phase and mobile phase. Okay, so these phases you have to remember these phases. Okay, which one is stationary phase and which one is mobile phase in this thin layer and gas liquid chromatography. Okay. Complete table 6.1 with an example of each of these. Okay, so in thin layer chromatography you have to tell stationary phase, which is an aluminum oxide L2O3, or you can and this could be silica. Okay, so you can write it as aluminum oxide or silica. Okay, so I'm writing there which is more common, which is aluminum oxide. And mobile phase in this gas liquid chromatography is an inert gas. Okay, any inert gas, for let's example argon or a nitrogen. Okay, so any inert gas, or you can just write as inert gas. Okay, so these mobile phases and stationary phases you have to remember them. Okay, part 2, an unknown amino acid is analyzed using thin layer chromatography. Two chromatograph graphs of the unknown amino acid and four reference amino acids PQR and S are obtained using two different solvents. Identify the unknown solvent amino acid. Justify your answer. So now, firstly, you have to see that the dotted the unknown amino acid has, which is equal to these amino this reference amino acids. Okay, so you can see that this amino acid in first solvent is equals to p q and s. Okay, sorry, q and s, and this, and then in second solvent you can see that this unknown amino acid is equals to r and s. Okay, in first solvent, solvent 1, you have this unknown amino acid is equals to q and s. Okay, and then in second solvent you have amino acid equal to r and s. Okay, so which amino reference point is common, which is s. So this must be the amino acid, unknown amino acid. I hope I could clarify. So identify the amino acid. So this is s, because rf value is the same as the unknown amino acid, is the unknown amino acid in both solvents. Okay, this is the reasoning. Moving towards next part, part G. A mixture containing 3 organic compounds is analyzed by gas chromatography, okay, and mass spectroscopy. Okay, the gas chromatograph gram is shown. Okay, the area underneath each peak is proportional to the mass of respective compound in the mixture. Okay, the concentration of K in the mixture is 5.52 into 10 to power minus 2 gram per dm cube. I can calculate the concentration in mole per dm cube of L. Okay, so you have concentration of K and the area underneath K is shown. So K, in K you have area at 44, you have this concentration 5.52 into 10 to power minus 2. Okay, now you have to calculate the concentration of L. So what is the area underneath L, which is 58? So what will be the concentration? So by cross multiplication you will get the value of X, which is going to be 58 divided by 44 multiplied by 5.52 into 10 to power minus 2. Okay, so from here by you will get the value of X, which is going to be 7.28 into 10 to power minus 2 gram per dm cube. Okay, this is concentration in gram per dm cube. Okay, but you have to calculate the concentration in mole per dm cube. Okay, so for mole, formula is mass upon mr or ar. So you just have to convert it into mole. You have to divide this concentration by mr of L, which is given to you. So 7.28 into 10 to power minus 2 divided by 116. So you will get the concentration in mole per dm cube 6.27 into 10 to power minus 4. Okay, I hope you understand this. Moving towards next part, part 7. Procaine is used an anesthetic in medicine. Okay, it can be synthesized from methyl benzene in 5 steps as shown. figure 5 7.1. This is the mechanism, this how you can make procane from this methyl benzene. Part A, name all the functional groups present in procane. Okay, so here you will have ester group, then you have this phenylamine group, and you have this amine group as well. Okay, so there is phenylamine, then you have ester group, and you also have amine group. This is a tertiary amine. Okay, a molecule of procane has 13 carbon atoms. Okay, state number of carbon atoms that are sp2 and sp3 hybridized in procane. Okay, so in sp you must have a triple bond, so there is no triple bond in procane. Okay, so no sp or carbon. And in sp2 you have a double bond, so you know that each carbon in this ring has a double bond, so 6 carbons, 1 2 3 4 5 6. And then this carbon with oxygen forms also a double bond, so 7 carbons have uh, sp2 or hybridization. Now you have 13 carbons, so remaining 6 will have sp3 carbon hybridization, and you can check from this uh, this formula as well. This 1 carbon 2, and then you have 3 4, and you have these 4 carbons. Okay, so 4 plus 2 6 carbons. Okay, moving towards next part. The proton NMR spectrum of procane dissolved in D2O. This is a heavy water is recorded. Okay, predict number of peaks observed. Number of peaks. This heavy water D2O removes the peak of an amine NH and OH. Okay, so there is no OH, but there is NH group, so this will not be count. Okay, so how many peaks will be shown? So you have to check the environment of hydrogen. Okay, so this is the first environment of hydrogen. Let's make this with red. Okay, this is the first environment. These both hydrogens have same environment. Okay, then you have a second environment, which is these two carbon or these two hydrogens attached over here. Okay, then you will have this these hydrogens. Okay, then these there are you have these 3 1 2 3. Okay, 4. Okay, so then you have this fourth environment, which is this hydrogen. Okay, this hydrogen is also in different environment. Okay, so there you have 4 environments, and these two hydrogens also have different environment from each other. Okay, this hydrogen has a different environment, and this hydrogen also has a different environment. Okay, so in total you have 6 different environments. Okay, so how many peaks you will get? 6 peaks. Okay, moving to our next part. State why procane can act as base. So in procane you can see there is a lone pair on nitrogen. Okay, let's remove this. There is a lone pair on nitrogen which can which it can donate to form uh, the, and the lone pair donors are basically bases, or it can accept a proton as well. So you can write lone pair on nitrogen can accept a proton. Okay, moving towards next part D. The compound X can be synthesized in two steps by from methyl benzene of compound X. Draw the structure of compound W in the box provided. Okay, so the structure will be this one. And why not this one, structure? Because this group, uh, COOH group, is a three director. If firstly we you if you think that if in W would be this group, so you will have a nitrate group attached on the third position. Okay, 1 2 3, you will have a nitrate group attached on third position in the step 2, but this nitrate group is attached on this fourth group. So I know that W will have a alkyl group, methyl group attached, because this is a 2,4 director. Okay, and this COOH is a 3 director. Okay, so you have to be careful over there. Okay, state the reagents and conditions for step 1 and step 2. So in step 1, but there is a nitration of alkyl benzene. Okay, so for the nitration you use concentrated nitric acid plus and sulfuric acid, concentrated sulfuric acid and nitric acid. And then in step 2 there is oxidation of this methyl group. Okay, and this happens by alkaline KMnO4, about alkaline KMnO4. These conditions you have to remember them. Okay, part E. Procaine is synthesized in 3 steps from X. Okay, this X, from X you can get procaine in 3 steps: step 3, 4 and 5. Okay, so suggest the reagents and conditions for step 4 and step 5. Reagents and conditions. So what is happening in step 4? In step 4, this benzoyl chloride group is forming ester. Okay, and you have this group attached. Okay, so what is the reagent? This is the reagent which is reacting with benzoyl chloride to form ester. Okay, so this must be an alcohol group. So CH2NO. So this is going to be a CH2 and N CH2 CH3. Okay, and this OH is attached over there. Okay, and then in step 5, sorry, in step 5, this this nitro group is changed into a amine group. Okay, phenylamine. Okay, so this is the basically reduction. Okay, when you reduce nitrobenzene, this form phenylamine, and the conditions for these reactions are thin plus and concentrated and concentrated HCl, okay, and heat also. These conditions you have to remember them, okay. Moving towards next part, part F. What is meant by partition coefficient KPC? Okay, this is the ratio of the concentration of solute in two solvents at equilibrium. Okay, two immiscible solvents. Ratio of concentration of solute in two immiscible solvents at equilibrium. Okay, the partition coefficient of protein between octane 1 ol and water is 1.77. Okay. Octane 1 ol and water are immiscible. A solution containing 0.5 gram of protein is in 75 cm cube of water is shaken with 50 cm cube of octane 1 ol. Calculate the mass of protein that is extracted into octane 1 ol. So the equation of KPC is a concentration of X in octane 1 ol. I am considering propanol as X in octane 1 ol and divided by concentration of X in water. Okay, we basically we in this formula water that this water is in denominator. Okay, the solvent water. Okay, so now you are given these volumes of water and volume of octane 1 ol, and in total you have 0.5 grams of protein in initially in water. Okay, so calculate the mass of protein that is extracted into octane 1 ol. Okay, so I'm considering this as X gram, okay, which is concentration. So we have to calculate concentration, okay, and because these are in concentrations. Okay, so concentration in gram per cm cube. Okay, so X divided by 50 cm cube. Okay, this is your concentration in octane 1 ol, and then you will have concentration in water. So uh, in water what will be X grams in octane 1 ol, and then you will have a 0.5 minus X grams in water. Okay, and what is the volume of water used? This is 75. Okay, and you are giving the value of KPC, which is 1.77. Okay, so from this equation you can find the value of X, and which is going to be the mass of protein extracted. Okay, so X is 0.271 if you calculate this. Okay, I think you will calculate this easily. 0.71. Okay, so that's the end of this paper. I hope everything is clear to you, and if you have any queries you can ask me in the chat box. I will try to give you the answers, and thank you for watching. If you haven't subscribed my YouTube channel, do subscribe. Okay, thank you.